Now we are ready to optimize our network. So let us open up a new code block for this task. We'll create a new network, and we want to perform optimization steps to fit the model parameters to the data of X train and Y train, of course. Well, let us do this part, and this is to compute the prediction of the output, and we can also compute the loss, but I think the loss function we haven't named it properly, because now here is the loss. If we have another variable of the loss, let's call the loss value. Okay. Loss value, loss prediction, and y. And then we take the derivative of loss and perform the backpropagation, and then we will have the parameters. Okay. We then want to apply those parameters to the neural network so that the loss could reduce. To apply them, we can simply let ML.W is change to the negative direction of the gradient. Therefore, the loss will reduce. dw actually we can save this tautology. We can just let it reduce. But please be reminded that the loss has been calculated with respect to unit change. But in practice, normally we do not want to change the parameters by a unit. That is way too large, because the neural network function is a nonlinear function. For a nonlinear function, you have the issue with this. If this is a linear function, and you find, okay, this direction, this is a way to reduce the value function. And okay, if you go this direction, the further you go, the lower the value of function will be. But on the other hand, if this is a nonlinear function, at this point, you may find, okay, this is the direction to which you want to reduce the value of function. But if you take a large step, if you take a small step, it's okay. You get the function value reduced a little bit. But if you take a very large step, you may go over this locally optimal point and into this region where you actually deteriorate the loss value. So for this reason, we introduce another concept, which is called learning rate. Let it be 0.1 or something like that, maybe a little bit bigger. So we let that to change by the rate of determined learning rate. And I just apply that to all the parameters. And then we can do the prediction again and calculate the new loss value and check whether it has been improved. Let's call that loss value new. Let's check It seems that there is a little tiny change. So how about let's check the difference. So we use the old value to subtract the new value. We subtract new value from the old value and see the difference. Oh, it seems that there is a little improvement in the overall performance. Maybe you can use a slightly larger learning rate and see how that. Okay, we have some improvement. What we need to do to get the optimal parameter, or at least the local optimal of the parameters, we will do this step over and over again. For example, we can do this while loop, make a loop of that. So we do not need to do this anymore because we will loop back. But we can have, for example, the iteration counter, and we print the iteration counter. And the corresponding loss value. Okay. We don't want to generate very large number of output which we cannot check clearly. See, we print for every 100 steps. And let us forcefully assign some maximum number of iteration. Say let the maximum iteration to be some large number, for example 5000. So let us see how that works. I think we have made a small mistake. We should print it out for every 100 steps. Instead, that means to check the mode to see this will be 0 when each counter is some integer times 100. So we should do this. Look, the loss function reduces nicely. Okay. In the next, I will use this function, draw landscape, to visually examine how the neural network worked on the landscape of the input space. Say if it requires a prediction function, and let's have a look. The prediction function need to accept the input, and then it will output the corresponding predictions, and which is exactly what our neural network do. Therefore, see, we don't want to make too many. Let's do this because I want to have a look at the initial landscape. draw landscape, and the prediction function will be our neural network dot forward. Okay, let's see how will that work. It worked nicely with a correct classification landscape here, but we haven't the chance to look at the previous pictures. Let's save them. Okay, it has a save figure option. We just need to provide the corresponding file name. That's good. Okay, let's finish running. Let's check the output pictures. Okay, initially, it's just a flat prediction over all the X space. After 500 training, look, it changed slightly because the prediction is not a 0-1 prediction. The prediction predicts the sigmoid of the last layer out linear combination, which will be interpreted as the probability of the samples belonging to the positive class. So the probability landscape now has a little change in color. If you check carefully, it is greenish here and yellowish here. Let's check for more steps. Well, now it is very well classified. Is there any intermediate step? Okay, this is an intermediate result where it starts to separating the two classes, but the classification is not so well separated. We can have a look at the corresponding loss function at this seemingly intermediate but it's a similar to start working step, which is 100. So it's about at this point the model starts working, and at this point the model starts working very well. Okay, and I think this demonstration has nicely explained the training of neural networks, at least for this toy example.